Last lesson, we introduced the risk mapping for equities. In this lesson, we will finish this section by examining the cash flow mapping of bonds. This is one of the key methods with which interest rate instruments are handled in VAR calculations. For a large bond portfolio, for practical reason, instead of assigning a risk factor for each bond price, the common practice is to use prices of zeros as standard maturities as risk factors. Here, the risk factors for bond positions are standardized to prices of zero coupon bonds with standard maturities, typically 1 month, 3 months, 1 year, 2 years, 5 years, 7 years, 10 years, and 30 years. Only the volatilities and the correlation data on zeros of such standard maturities need to be collected, which is typically collected and maintained in a value at risk system. For illustration, consider a portfolio of Treasury notes or Treasury bonds. We first treat each note or bond as a portfolio of its constituent zero-coupon bonds. The position in each of the zero-coupon bonds is then mapped into an equivalent position in the adjacent standard maturity zero-coupon bonds. When the mapping is complete, we will have an equivalent portfolio of zeros at the standard maturities, from which the VAR can be computed via the delta normal method. Then, the VAR of the original bond portfolio is simply the VAR of the portfolio of mapped equivalents in zeros of standard maturities. In the following, we will illustrate the mapping procedure by showing how it is done for zero and non-standard maturity. Suppose we have a 6-year zero and that the adjacent standard maturities are 5 years and 7 years. How to map this 6-year zero to the 5-year and 7-year zeros? Here are the criteria. The values of the two mapped zeros are weighted such that the following three conditions hold. First, the market value is preserved. Second, the market risk is preserved. And finally, the sign is preserved. Let Zi denote the present value of the I-year zero. Then the cash flow mapping from the 6-year zero to the adjacent 5-year and 7-year zeros is arranged as follows, where beta is the proportion allocated to the 5-year zero, and is to be determined. Let Yi denote the yield for the I-year zero. Apply the linear interpolation, we obtain the interpolated 6-year yield, which will be used to determine the present value of the 6-year zero. Here, gamma is proportional to the relative distance between the maturity of the mapped instruments and that of the reference instrument. In this example, gamma is equal to 0.5. Since Z6 is expressed in terms of beta portion of Z5 and 1 minus beta portion of Z7, from the portfolio theory, we get the following expression of the variance of Z6 in terms of the variances of Z5 and Z7, where ρ57 is the correlation coefficient of Z5 and Z7. If sigma 6 is somehow known, then beta can be solved from the following quadratic equation, which is simplified from the above expression. One way to estimate sigma 6 is to apply linear interpolation, same as the estimation of Y6. Once beta is solved from the quadratic equation, the cash flows mapped to the adjacent standard time vertices can then be obtained. In this case, Z5 is equal to beta times Z6, and Z7 is equal to 1 minus beta times Z6. Here's an example. Consider $1 million position on a 10% Treasury bond with 0.8 years to maturity. Coupons will be paid in 0.3 and 0.8 years, and the principal is paid at the maturity. Determine the 10-year 99% VAR by cash flow mapping using the following information on 3 months, 6 months, and 1 year zeros. Note that the bond price volatilities are given in percentage per day, and also the correlations given are on daily returns. Since the bond has principal $1 million and coupon rate 10% paid semi-annually, it can be considered as having a $50,000 position in a 0.3-year zero and a $1.05 million position in a 0.8-year zero. Those zeros have to be mapped to the 3 adjacent standard maturities. With the given yield rates of the 0.5-year and 1-year zeros, the yield for 0.8-year zero can be estimated via interpolation. Then, we can calculate the present value of the $1.05 million position 0.8 years from now. Same as the yield rate, the 0.8-year volatility is also estimated via interpolation. If beta portion of the 0.8-year zero is to be allocated to the 6-month zero, then we have the following equation, which can be simplified to a quadratic equation of beta as follows. Solving beta leads to 2 roots, and we'll choose the one in between 0 to 1. Hence, the 6-month zero is allocated present value of beta times $997,662, and 1 year zero is allocated the remaining. Similarly, we can obtain the mapping result of the 0.3-year zero to the 3 months and 6 months zeros. And thus, the 2 cash flows involved in the treasury bond are mapped to the 3 standard maturity zeros. Here's the covariance matrix of the 3 standard maturity zeros, which can be computed from the given volatilities and the correlation matrix. Together with the cash flow vector obtained from the mapping, we can calculate the 10-day 99% VAR of this treasury bond as follows. As a summary, in this lesson, we have examined the cash flow mapping approach for the estimation of bond VAR. And that is the end of this chapter.